Good evening, everyone. Welcome to Boise State's Physics First Friday Astronomy. My name is Heidi Wu. I am an assistant professor in physics at Boise State, and I'm your host tonight. I'd like to start with a few announcements. Next month, we will be joined by Dr. Johanna Teskey from the Carnegie Earth and Planets Lab. She will talk about the current and future landscape of small exoplanet demographics. As you probably know, the James Webb Space Telescope is scheduled to be launched in December. And this lecture is part of the James Webb Community Event Series. Dr. Teskey will share with us the exciting exoplanet research she has been doing and will be able to do with James Webb Space Telescope. And in this evening's talk, if you'd like to ask questions, please use the chat feature here on YouTube. And I will be monitoring the chat and then relay the questions to our speaker. This evening, I'm very excited to be introducing Dr. Yao-Yuan Mao from Rutgers University. Dr. Mao received bachelor's degree from National Taiwan University and PhD from Stanford University. He received Langley Pitt PACC postdoctoral fellow at the University of Pittsburgh and is currently a NASA Einstein Fellow of the Hubble Fellowship Program. This fellowship program is one of the most prestigious awards for postdocs in astronomy. Today, I'm very excited to learn that Dr. Mao will join University of Utah as an assistant professor next summer. He will be in our neighborhood. Congratulations. Dr. Mao is a world expert on the research of the so-called dwarf galaxies. He has created highly accurate simulations for dwarf galaxies and has led large observation programs for these galaxies. Dr. Mao has answered many important questions about dark matter and galaxy formation using these dwarf galaxies, which he will share with us tonight. In addition, Dr. Mao has played multiple important leadership roles in the Vera Rubin Observatory's dark energy science collaboration, and he has helped creating an inclusive and equitable science community. Please join me in welcoming Dr. Yao-Yuan Mao.
Thank you, Heidi, for the kind introduction. I will be sharing my screen now. All right, hopefully you will be looking at my screen. Do let us know if there's any issues. And good evening, everyone. I'm really happy to be speaking with you, talking about something called dark matter and how they connect to galaxies. And so you can see from my title and the picture that I show on my title slide that the two subjects we'll be talking about are dark matter, which we will go into the detail of how they make up the kind of the underlying structure of our universe, and also a wide array of different types of galaxies. So we will start something really close to home. So you're looking at a picture taken from Chile near the Blanco telescope. What you're looking at is the so-called Milky Way. So this is the center of our very own galaxy. You can see the beautiful Milky Way across the sky. On the left, you can also see two small blobs. These are the so-called large and small Magellanic Clouds. They are other smaller galaxies that are orbiting our own Milky Way. So all these larger and smaller ones are all galaxies. But where we are in this picture, so if I zoom out a little bit and kind of bring us to the outer space, we are looking at the rendered, artist rendered version of the Milky Way. Our solar system is here. And so in the previous picture that you just saw, the Milky Way is kind of what you can see in the night sky from looking toward the center of our Milky Way. The two small blobs earlier that I showed you are something that is orbiting our Milky Way. So they're outside of this key structure that you see here. So let me zoom out a little bit more. So that Milky Way that you just saw, now it's at the very, like at the kind of lower center of the picture here. And you can see, besides the large and small Magellan Clouds that I mentioned to you earlier, there are actually tons of other galaxies that are also orbiting the Milky Way. A little bit further away, this is the Andromeda Galaxy, or M31. And you can also see tons of galaxies that are orbiting the M31. The system you're looking at here, the combination of Milky Way and the M31, we call it a local group. And this is actually part of a larger cluster that we call the Virgo cluster. So if I zoom out even more and kind of turn our lenses to the outer space, this is a picture taken by the Hubble Space Telescope. On this picture, mostly what you see are galaxies. There are a few stars, but besides those things, the majority of the bright points that you see are galaxies. Some of the galaxies are nearby, and so you can kind of see the spiral structure in those nearby galaxies. Some of the galaxies are really far away, and so to you, they are just really a single point or a very fuzzy blob that you saw. And this is kind of what the space would look like in the optical wavelengths. You basically see many, many galaxies sprinkled in a very empty space. But what happened if I can kind of turn, I don't know if I say turn on the light or turn off the light, but be able to see dark matter. So what is dark matter? So we know the universe have about 5% matter that we call the visible matter or normal matter. And about 27% is something that we call dark matter, and about 68% of something that we call dark energy. And so dark matter is something that I will be focusing today. And so as I say, if we can turn off the light and be able to see dark matter, this is what the universe will look like. So this is a very different picture than the one that you just saw with the galaxies. Instead of those disconnected points that you saw earlier, what you see is kind of like a web structure. We call it a cosmic web. This web structure is created by this filament structure that is formed by the dark matter. The filamentary structure actually intersect with each other and then create these high density regions. So the bright spot that you're looking at are the very high density region of dark matter. We give the name of dark matter halo. We'll go into this a little bit more later. But all these high density region or dark matter halos are the places where we believe the galaxies are forming. So now I play kind of a movie that shows how the previous pictures evolve with time. So at the very beginning of the universe, everything seems to be very smooth. And you start to see the contrast in this movie. You see the filamentary structure being formed. You start to see the bright spot, the high density region of dark matter. You can see the high density region kind of start to have orbital motion, orbiting around each other. And they actually merge and they become brighter and brighter, which just means the density becomes higher and higher. And eventually you will see the kind of the web structure that we just saw in the previous picture. And everything you see in this current movie are from the motion of dark matter and the expansion of the universe only. We didn't actually take into account all the complicated physics from the normal matter yet. But again, the formation of the galaxies are believed to form together with the formation of dark matter. And through the merging of the dark matter structures, the galaxy also form in those bright spots that you see in this movie. So maybe the first question you might ask at this point is, how do we actually know galaxies live inside this dark matter halos that I just mentioned earlier? To explain this to you, I want to actually quote this sentence from Frederick Bessel. he says the visibility of countless stars is no argument against the invisibility of countless others. I really like this quote. And this the context of this quote is actually when they discover a binary star system. And the binary star system, one of the binary stars is really faint. And so they cannot at the time, 1898, they cannot actually observe the companion. They only observe one of the two stars. But they see a motion of that bright star. And so Friedrich Bessel argued there must be another companion, and that is why the bright star have a kind of orbiting motion. And so that is how the context of this sentence. And so while this sentence coming from the discussion of stars, it's actually kind of the same reason why we believe galaxies are living in dark matter halos. So I do have some equation in my presentation just for those who are interested in mechanics, but I assure you, this equation, not understanding this equation will not impact your understanding of the presentation itself. But if you consider a two-body situation where you have two mass points, mechanics actually tell us in an orbiting system, the velocity of the object actually can help you infer the mass of the other object. And so this is actually really important. By measuring the velocity of an orbiting object, you can kind of infer the mass, the object that is orbiting around. So if we take that the particular understanding from the mechanics, then we can actually try to measure the rotation velocity of the stars in the galaxy. So again, you're looking at the galaxy, a picture of a galaxy, and all the stars here actually are orbiting around a galaxy, kind of along this spiral structure. And astronomers are actually being able to measure the velocity by using something called a Doppler effect. And this is basically how kind of the speed radar gun works when you are speeding on the highway. And so what we can do is now can measure how fast the stars are orbiting around a galaxy as a function of the radius of the galaxy. And this is shown in a picture from the original plot measured by Vera Rubin in 1978. And you can see the rotation velocity goes from like very small near the center to kind of flatten out to some certain speed at the larger radii. So remember what I just told you, that if you measure the orbiting motion of something, it can tell you what is the mass of the things that is orbiting around, right? And so by measuring rotational velocity here, you can kind of infer the mass that the enclosed object must have. So we now have two things. We have the velocity, which infer mass, but there is also light that you see from this picture. And from the light, you can also infer the mass. And so if I calculate the enclosed mass from the visible matter, which is the light profile that you see here, and then you can do some calculus and you can get this equation. Again, the equation is really not important because I will plot the equation for you. This is what the expected rotation velocity would look like, just by calculating the light that you receive from this picture. But you just saw me earlier show you the actual rotation curve. It kind of flattened out at the larger radii. And so the question is, what is actually making up this difference, right? This tells me that there must be some other mass that I'm not seeing, so that the velocity is actually much larger at larger radii. And that is actually what we call the dark matter or the missing matter. We think that there are something that we don't know what it is, but have mass. That is kind of the galaxy kind of embedded in that. And so that is why at the larger radii of the galaxy, the stars are moving much faster than what we expected from only the visible matter. But that is actually not the only evidence that we have for the existence of dark matter. So here I'm talking about something that's completely different. Again, you are looking at the galaxies. These bright spots are all galaxies. But what I want you to pay attention is to the arc structure around those galaxies. You can kind of see here, there is a few here as well, and here. These things are the gravitational lensing effect. And this is caused by a very, very heavy mass that is heavy enough to bend the light. And so you have galaxy cluster that you have the light. And then the background galaxy, its light travels through the galaxy cluster to reach us. By calculating how much light bends by measuring the arc that I showed you earlier, you can actually also infer the mass that must contain on the path of the light travels through. And actually, again, the mass is much larger than just the mass from the visible matter. And so that is another evidence that there must be some missing mass in galaxy systems. There's another evidence actually coming from, again, a totally complete context from the cosmic microwave background. So the cosmic microwave background is something that we can measure to tell us kind of the earliest history of the universe. You are looking at kind of the visual representation of the evolution of the universe, all the way from the Big Bang on the left to the current stage of the universe. And so you can see the universe goes through kind of the Big Bang, and this is the so-called last scattering. That is actually kind of, you can imagine that as a picture of an early universe that we can still see today. And this picture, why does this picture tell us about dark matter? Because remember the early movie that I showed you? You see the dark matter structure kind of collapse onto each other and form the high density region. Somehow the dark matter and dark energy act very differently, and how that in the evolution of the universe, dark matter pulls things together and dark energy kind of push things apart from each other. And by measuring how much the microwave background evolved, you can actually then put some constraint on the ratio of dark matter and dark energy. And that ratio actually will show up in all the kind of patches that you see earlier in the previous picture. And if I kind of try to quantify this kind of patches that you see here, this is a way that we quantify that. We show something called the power spectra. The detail of the mass is not really important, but I just want to show you by inputting specific ratio of dark matter, dark energy, and the ordinary matter, we can actually make a very precise prediction of how the power spectrum should look like. That is a red line. And it just match really beautifully to what we actually observe from the real universe. And so combining all these things, most modern astrophysicists really believe there is the existence of dark matter, or at least there's something that we don't know what it really is about, what it really is. So we do know a few things. We do know that dark matter is not any matter that we already know about. It's not light, it's not atom, it's not electron, etc. And we know this by, again, several of the things that I mentioned, including the cosmic microwave background. We know that if it's something that we actually already know about, then the wiggle that you just saw earlier in the previous picture will not actually behave the same. We also know that dark matter hardly interacts with anything we know. It doesn't interact with light, it doesn't reflect or absorb light. It doesn't really interact with normal matter at all. That being said, we are still trying very hard, and we are kind of hopeful that there has tiny interaction between dark matter and normal matter that we can make us to actually detect dark matter. And there has been several major ways we have been doing to try to find out what is dark matter. And so in this very cartoonish picture, it actually nicely depicts three major ways that we do to find out what's dark matter. One of them is called direct detection, which is shown here. We put a detector deeply underground. And because dark matter do not usually interact with other matter, so it can kind of penetrate the Earth and reach the detector, while other normal matter cannot. And so the hope is that, even though with very, very small probability, maybe dark matter will interact with something in the detector, and then we can see a signal. The second major way is called indirect detection. This is by looking at, again, into the universe, in particular in regions where we believe there's high density of dark matter. And here we are hoping that dark matter will, kind of collide with themselves and self-annihilate and create something called gamma ray. And then by detecting the gamma ray signal, we can say, okay, maybe there is a high density of dark matter so that we can see the annihilation signal. The third major way we have been trying to do is called the collider production. This is particularly be done in a large hadron collider in Geneva. And this is kind of the opposite of what we just said. Here, we kind of smash no matter, in this particular instance, protons together. And we hope to create large enough energy so the proton annihilate with each other and then generate dark matter. So all this major experiment has been carried on for decades and trying to find dark matter. And you might ask, have we found dark matter yet? Unfortunately, no, not yet with any of these three particle methods. We have a lot of evidence from astrophysical observation I showed you earlier, but we haven't been able to detect dark matter through these three particular methods. That being said, actually, you can buy dark matter on Particle Zoom. I actually have one with me just right here. I think it's $11. And if you got that, you can just claim that you have found dark matter at your home. So even though we haven't found dark matter, it doesn't actually prohibit theorists to come up with all the beautiful idea of what dark matter might be. Here again, beautiful cartoon to show different kind of dark matter. I'm actually not going to tell you what each of this is. The idea of showing this picture is that different type of dark matter actually have different behaviors, as shown by this cartoon. Some dark matter like to play with themselves. Some dark matter actually interact with each other. And the hope, actually, of my research is that by doing some astrophysical observation, we can actually try to distinguish these different models of dark matter that theorists come up. And this turns out to be a very challenging task. And so I will go into a little bit more detail why it is difficult and then what we have been doing to try to solve this problem. So how do we go from astrophysical observation to the concept of dark matter? So first thing that we need to realize is what I just told you. The galaxy actually live inside those dark matter structure or dark matter halos. The simulation that I showed you earlier is really closely related to all the theory that I just showed you in the previous picture. We can simulate the different type of dark matter and they actually create different structure in the simulation. Galaxies, on the other hand, is something that we actually observe. They have very rich property, and we actually live in one, right? As I just showed you at the very beginning, we live in the Milky Way galaxy. And so if we can have a way to connect the galaxy that we observe with the dark matter halo that we simulate, then we can use the observation to put constraint or basically to try to get better understanding of the underlying dark matter model. And so this is kind of trying to demonstrate what I just showed you. Here you are looking at the structure of the universe. On the upper left, this is the actual universe that we observe. On the lower right is a simulation. And then we kind of pen galaxies onto the dark matter simulation. And so what I'm trying to show in this picture is that the simulation actually can quite truthfully produce what we actually observe in the universe. And so if we can understand the connections between galaxies and dark matter even better, then we can, by comparing the slight differences between these two pictures, get a better understanding of what kind of dark matter we should put into the simulation in order to make the two pictures as close as possible. Now, before we go into even more detail, I kind of mentioned galaxy and dark matter, but I want to really put things into scale for you. So when I talk about galaxies, the galaxy is really small compared to the structure of dark matter or the dark matter halo. Typically speaking, for a Milky Way galaxy, the radius is about maybe 70,000 to 100,000 light years. And that is about only 1/10 of the typical size of the halo, the dark matter halo that is hosting the Milky Way. And so in this picture, this Milky Way really lives at the very, very middle center of the dark matter halo. And you can see here, there's many other density peaks, the bright spots, that is actually within the dark matter halo. And so I just want to define a few terms so that it's easier for us to refer to as we move on. So this whole thing, we call it the dark matter halo. And the galaxy live, again, at the very center of the dark matter halo. The other density peaks, we usually call it the subhalos. It just means a halo live inside another halo. And again, we also believe there are galaxies live in those subhalos. Sometimes we call that satellite galaxies. The term satellite galaxy really has nothing to do with the artificial satellite, but it does have the same meaning in the sense that the satellite galaxies are orbiting the main galaxy, just like the artificial satellite orbiting the Earth. And also as theorists, as physicists, actually, we all want to believe everything's spherical. So usually we think that dark matter halos are spherical. They are, really not an object. They're kind of fuzzy, but we tend to think, tend to use this kind of spherical representation to show what dark matter halo is. Okay, with all the term explained, then we come back to this picture I showed you earlier of local blue and satellites. Now, with the picture that I showed you just a little bit earlier, you can now understand the Milky Way actually live in a larger dark matter halo, and the satellite actually live inside a subhalo that is orbiting the Milky Way. And similarly, for M31, there's large dark matter halo around M31. In fact, we know that M31 and the Milky Way, the dark matter halo actually roughly touch each other. And similarly for M31, the satellite galaxy live inside the subhalos, then orbiting the M31 or Andromeda galaxy. So why is the satellite galaxy interesting? Because it turns out these little galaxies are particularly sensitive to different dark matter models. And so here I'm showing you three particular dark matter models. The cold dark matter, this is kind of the standard dark matter model that we have been using. In the middle one is self-interacting dark matter. That means the dark matter particle themselves have some self-interaction. On the right is warm dark matter. It means the dark matter moving at a much faster speed compared to the cold dark matter. Again, remember you are looking at the halo that is, the size that hosts the Milky Way. So the radius is about 1 million light years, which is about 10 times of the Milky Way size. The Milky Way, if a Milky Way lived in one of these halos, it would really live at the very center of the halo. And all the bright spots that you see around the center are the substructure that are hosting the satellite galaxy. And so immediately from this picture, you can see if our universe, the dark matter actually is coming from one dark matter, then there are much fewer substructures or subhalos, which means that we should see much fewer sub-satellite galaxies orbiting the Milky Way. For the self-interacting dark matter, you may not be able to see by eye immediately, but actually the density contrast is a little bit lower compared to the cold dark matter, and that also affects what kind of galaxy the subhalo are hosting. So coming back to this picture again and again, by starting the satellite galaxy orbiting the Milky Way, we can kind of compare with what we simulate and trying to understand the formation or the composition of the dark matter. But you might ask, actually, how representative is Milky Way? Is our Milky Way? Like Milky Way is one such system. How are we sure that by studying just the Milky Way satellite, we can be certain that our interpretation of the dark matter model is accurate? And so this leads to this project that I've been working on in the past almost 8 years called the SAGA Survey. And so I want to give you a little bit of context here. So in the Milky Way is like where we live. So it's closest to us. So we can really find a lot of satellites. It's not that there are more satellites in the Milky Way. It's just that they're closer to us. So we kind of can see fainter objects that are closer to us. Once we move out to M31, which is our neighbor, Andromeda, and because it's slightly further away, we cannot see as faint. And so we only see about 25 satellites in the M31. Again, it's not because M31 has fewer satellites, it's just because it's further away. So we cannot, go down to as low luminosity as our survey limit. If I go even a little bit further, step out the local group into local volume. So this is within 20 megaparsec or 60 mega light years. Then again, these things become even further away and become even fainter. And so we can see fewer satellites in those satellite systems. If you go even further away to the observation from the Stone Digital Sky Survey, then you can actually at most see one satellite in each system, because all the rest are just too faint to be detected. So the SAGA survey is trying to do something in between. We want to get enough objects to get a representative sample of Milky Way-like system, right? We don't want just 1 or 2 or 6. We want to get around 100 systems so that we can have a representative sample of Milky Way-like systems. At the same time, we want to be close enough so we can probe at least 3 to 5 satellite objects per system. So that is pretty much our goal. And so what we do is that we go out to find Milky Way-like galaxies. So here is one of the example. And remember, Milky Way galaxy live at the very center of a dark matter halo. Dark matter halo is much larger, if you remember what I just told you. And then what we are trying to do is to find the satellite galaxy within that region of the corresponding size of dark matter halo. And so the survey would pretty much patches on the sky, right? We find one Milky Way galaxy, and then we kind of try to search for the satellite in the vicinity of that Milky Way galaxy. So you might ask, why is this difficult? And this is difficult because we're seeing that field of view. Again, here the center is the Milky Way galaxy, and all the other points are the background galaxy in the field of view. When you look out, we cannot really distinguish whether a galaxy is a nearby galaxy or a background galaxy. And most of the time, it's a background galaxy because guess what? When you look out, the background universe just have a much larger volume compared to the nearby universe. And so the difficulty is to from all this background galaxy, there's actually about 2,000 something per square degree to find the actual satellite galaxy, which is on average only 4 objects per square degree. So we're going to about 2,000 something objects to 4 objects. And in order to do that, we have to make some pre-selection, because to measure the distance of objects is really expensive both in terms of money and the time to get a proposal written and get telescope time and to actually observe them. And so we need to be able to do some pre-selection so that we are not measuring a distance for all objects. So a lot of the work in the SAGA survey is to come up with clever pre-selection criteria. We did something so that we can cut the object to about 1,000 per square degree. And then in the last round of our work, we were able to actually even cut that to about 200 square degree. And from there, we really cannot distinguish whether some of this background object or nearby object. And then we have to do spectroscopy follow-up or measuring the actual distance of the objects in order to confirm if they are satellite or not. And in a nutshell, this is what we do. Basically, we are asking if a galaxy is a background galaxy or satellite galaxy. And to just really convince you how difficult it is, here are the 5 objects that in our survey. And only one of this is a satellite galaxy. The other 4 are all background galaxy. And you barely cannot distinguish which one is which. They all look pretty much the same. If you are interested to know which one it is, you can ask this question and I will answer to you after my presentation. And so by doing this, we have actually completed our census of the satellite system around 36 Milky Way siblings or Milky Way-like galaxies. Again, in each of this panel, you see the Milky Way-like galaxy at the center. The gray circle roughly depicts the size of the dark matter halo of the corresponding dark matter halo, and the colored circle are the satellite galaxies that we found. You really cannot see anything inside the color circle just because they are so faint. They are not actually being shown on this picture, but there are actually a small galaxy in there. And so from this picture, you can see, in some system, there are like 9 or 10 satellite galaxies that are orbiting. And in some system, there is really none, 0 or 1. And this is really important to know because then we can put the Milky Way into the context, into a kind of a cosmological context, and understanding whether our Milky Way is kind of spatial or not, or like it's really kind of in par with all the other Milky Way-like systems that we found. Here are the beautiful image of the galaxy, the satellite galaxy we found. I kind of grouped them into each system. So like for one system, you see there are like 10 satellite galaxy. In this system, there are 7, etc. As I said, we have 2 systems. We found no galaxy, no satellite galaxy to our survey depth. Really, the main reason I'm showing this plot is because they're really beautiful. You can see the variety of different galaxies from, spiral. There are actually sometimes the satellite galaxy could still have spiral structure, to kind of the fuzzy, large magellanic cloud-like galaxy, if you remember the very first picture that I showed you in my talk, and also to some of the very faint object, it's just a blob. And this variety of galaxy also teach us about the formation of the galaxy itself, how the galaxy gather their stars, forming, evolve, and then when they're being kind of captured by the main galaxy, how the star formation cease once they are being captured. And so there's a lot of rich physics that we can do with these galaxies beyond the study of the dark matter. So this is what we published earlier this year. We call it our stage 2 data release. And we are now working on prepare our stage 3 data release. We haven't finished yet. We are hoping to publish this next year. But I just grab all our existing data to date and show you what we have right now. And so at this moment, we have completed our survey in 97 Milky-like galaxy systems. And we have identified 334 satellite galaxies. And so this is a similar picture from what you just saw earlier, but you can just see, we are able to survey, so many systems and find so many satellite galaxies. Again, you see satellite systems that have, 10, 11, 12 galaxies to 1, 2, or 0. And this beautiful variance that you are seeing here really teach us something about the galaxy formation and dark matter. So today I'm not going to talk too much about galaxy formation. There's a lot to be said about that. But because of my talk title, I think I want to spend a little bit more time on kind of how do we use the result that we got from the SAGA survey to test different dark matter model. There are many different ways to do this. One of the ways is just by counting the number of satellites. So from the previous picture, you can count the number of satellites per system in the SAGA survey. And then you can plot a histogram to say how many satellites you are expecting per system, right? So like here, the way to read this plot is say there are 3 systems that have 0 satellite, 3 systems have 1 satellite, 9 systems have 2 satellites, etc. And once you measure this, you can now also ask in the simulation, what is the distribution you are expecting? And so we run simulation that are similar to this Milky Way systems. There is actually a difficult part that I didn't really describe, that is from the simulation. You also need to understand the connection between the dark matter halo and the galaxies, and then put galaxies into the dark matter halo in order to really make this plot. And that is whole by itself another 2-hour talk. But by doing this, you can then actually make a prediction of what this distribution should look like. And by studying the deviation between the observed points and the distribution from the simulation, you can then put constraint on whether or not the dark matter model that you put into the simulation is consistent. So for now, we still find the cold dark matter scenario is pretty consistent with what we observe. And we are trying to, using the more data that you just see that, this is only with 36 systems. We haven't done this for the 97 system yet. But our hope is to redo this study and see if we can learn more from more systems we have already observed. So that is by just counting the number of satellites. Another way to use the satellite system to distinguish different types of dark matter is by looking at the spatial distribution of the satellite. So we haven't done this work with the observational data yet. This is kind of a proof of concept that we actually just published a paper in FJL. Showing you the distribution of the satellite in 4 different models: cold dark matter, warm dark matter, self-interacting dark matter. And this one is still cold dark matter, but we put a central galaxy disk into our simulation and try to see if it has certain effect. And what you can see is that there indeed are different spatial distribution. Earlier you already learned that in the warm dark matter case, you have fewer substructure. And again, you see that here. In the self-interacting dark matter case, it turns out that the large magellanic cloud that I mentioned to you earlier the inflow of the Large Hadron Cloud actually kind of disrupt the subhalo along the trajectory. And so the subhalo distribution actually also change depending on how the LMC is falling into the Milky Way. In the galaxy disk model, you have fewer satellites near the center of the galaxy because of the disruption coming from the galaxy disk. But again, this is kind of a proof of concept to say that the data that we collected from the SAGA survey by doing some statistical analysis can also potentially be used to put constraint on different dark matter model based on the spatial distribution of the satellites. So, I'm really excited about this work because it's really nice to be able to understanding how our Milky Way stands in a much larger cosmological context. But also by doing this work, we are able to learn more about the fundamental of the dark matter and also the formation of the galaxies. So with my last few minutes, I actually want to take a step forward to say, the SAGA survey is actually already at the stage 3, right? I show you 97 Milky Way-like systems, the beautiful mosaic of all the satellite galaxies. So what do we do after the SAGA survey? And so I've been working on multiple, even larger survey collaborations. On the left, you're looking at the dark energy spectroscopic instrument. So this is a spectroscopic survey, which means they're measuring the distance to the galaxies. And so it's more like what we do in the SAGA survey in terms of measuring distance. But the focus of the dark energy spectroscopic instrument, as the name already suggests, is to measure dark energy. And the first year survey is already ongoing. They have generating amazing data from DESI, the dark energy spectral instrument, usually known as DESI. And I have been participating in this by using some of their spare fibers. So they are measuring the ratio to many objects to measure the dark energy. But as you know, I'm more interested in dark matter. They somehow have some of the fiber that are not used in their survey. And so we have been putting some of the spare fibers into this particular little galaxies that I have been mentioning to you to try to understand their properties and put constraint on dark matter. On the right is another thing that I'm actively participating in is the Vera Rubin Observatory Legacy Survey of the Space and Time. This is currently being constructed in Chile. The camera of the Vera Rubin Observatory will be the largest camera that has ever constructed. And this is actually a 3.2 gigapixel images of they taking a historic picture of Vera Rubin herself. This is not a spectroscopic survey, which means it doesn't measure distance. It only gives you the picture of the universe. It doesn't tell you how far the things are in that picture. And so remember earlier, one of the main challenges of the SAGA survey is to go from the image itself, which you don't have any distance information. You have all the galaxies there, you just don't have the distance information to find the satellite galaxy. So one of the things I'm doing is to combine the power of these two surveys and try to use the information we got from DESI and then in the future use to infer the distance for things that we observe with the Rubin LST. That means we are not going to be able to, we're not going to need to measure distance for each individual object in the Rubin LST survey. But by using the information we already know now, we can kind of build algorithm to try to tell the distance without actually measuring it. And so here's a sketch of how we actually do this. So you are again looking at the image from the SAGA survey. You have the satellite galaxy, you have some low redshift. Low redshift just means nearby background galaxies. The number you see here is kind of a cosmologist's way of measuring distance. The Z stands for redshift, and the larger number you see here, it just means further away. Okay. And there are some number about their photometric property, which is really not important here. But what I'm trying to show you is that the image itself actually contains some information about the distance. It's really difficult to see by eye, as I showed you earlier. But with some advanced machine learning algorithm, we can actually extract some of the information from the image itself. And so we have been using the deep learning algorithm to train on SAGA data and to effectively select likely nearby objects. And all these objects, we then use the DESI fiber that I mentioned to you earlier to follow up, to confirm if the deep learning algorithm is working. And I'm really glad to say, from the current data we have getting so far, the algorithm has been working really great. And so the idea is that with this data and algorithm, we will be able to come up with advanced algorithm that we can use to distinguish very close by galaxies using the Rubin LST data, which doesn't contain the distance information, but by looking at the image itself, we can infer the distance based on what we already learned from SAGA and DESI. And so all these things is useful. Why? It's because there's a lot about dark matter science that we can do with the Rubin Observatory. And so with a few colleagues, we have been sketching out all the possible ways that a Rubin Observatory can potentially help us to understand dark matter. And this is a kind of a small portion of a giant plot that we made to show kind of different type of measurements and how they put constraint on different type of dark matter model. And I just want to highlight one of those things, like the satellite luminosity function. So this is something similar to what I mentioned about the SAGA satellites, and those can help us to put constraint on a few different dark matter models. But this is just one of those things. There are tons of other galaxy and also stellar observation that we can do from Rubin to help us understand dark matter. And a lot of this depends on our understanding of the connection between galaxies and dark matter halos, and how to get a precise measurement of the distance to the galaxies that we found in the Rubin LST, the Rubin Legacy Survey of Space and Time. So with that, I will just tell you a few takeaways that I hope you will learn from this talk. We don't really know what dark matter is still, but I hope that I convince you by studying the galaxies, it can actually help us to trace out the dark structure underlying in the universe and help us better understanding the dark matter. And there are many, I hope I convince you dark matter really should exist based on multiple evidence, including the rotation curve of a spiral galaxy, but also like gravitational lensing, cosmic microwave background, so on and so forth. And particularly the little galaxy actually contain particularly useful information to tell the different dark matter structure. And little galaxy usually happen to live inside a larger dark matter halo. So they are satellite galaxy. And by studying those close to the Milky Way and also those in the Milky Way existence, we can learn a lot of more information about these little dwarf galaxies. And combining all these things with the future and current observation, including DESI and Rubin, we are hoping to map out the nearby universe in a more precise way, and that will in turn help us to better understanding the dark counterpart of the universe. So thank you so much for your attention, and I welcome any question you might have.
Great, thank you so much, Yao. So I will use my host privilege to ask my questions first.
Sure.
Yeah, so yeah, you show that in some of the SAGA galaxies, you found spiral galaxies as satellites. Does it mean that you actually have spiral little dwarf galaxies, or are those actually big?
Yeah, so
spiral satellites.
They're very big spiral satellites. They are not dwarf galaxy in that sense.
So are they like binary spiral galaxies?
Yeah, so I mean, some of those cases more like M31, M33 system, where M33, well, it's not really spiral, but they are really bright. We wouldn't call M33 a satellite. No, M33 is indeed a satellite galaxy, but we wouldn't call it a dwarf galaxy, right? And so in some of the SAGA system, they are indeed you have like really bright kind of spiral structure. And so it definitely means the overall mass of that system is much higher. It's kind of higher compared to the Milky Way.
I see. Well, yeah, that's very cool. Thank you. Actually, if I may, there's actually have another question. So you mentioned that the like the dark matter halo of Milky Way and then Andromeda are like almost touching. How do we know that? Do we just by is that by satellites? Like, yeah, how do we know that? We can't do gravitational lensing from them, right? So obviously,
no. We know
yeah.
that just by inferring. We know the distance to M31, and we know roughly how big the Milky Way halo should be, and we also know how big the M31 halo should be, and that is why we know that they kind of touch each other.
I see.
It's only by inferring the numbers.
Okay.
It is an interesting question that actually we want to answer, is to understand, people have been studying satellite galaxy. There's another field of study of people study isolated galaxy. Recently, I started to be very interested in galaxies that are near the kind of the middle points between Milky Way and M31. We haven't had much observation actually of those objects. And it's to be interesting to see if they kind of experience certain tidal interaction between the Milky Way and M31. And so we are thinking if we can do some of this both within the local group and also like kind of in the SAGA context outside of local group, but find local group like pairs and try to find satellites in between the two main galaxies.
Wow, that is so cool. Thank you. And we have a question from Titus here on the Zoom. Titus, would you like to unmute yourself and ask?
Yeah, okay, thank you. Like there was this picture you showed, like I think there were about 5 pictures, and then one of them was a background galaxy, and then yeah, like can you like explain further, because I don't really see the difference. Like how do we know?
Yeah, great. So in this 5 picture, only this one is a satellite galaxy. So this is closer, and the other 4 are background galaxies. So the other 4 are further away. And so you might ask, like, is this just, I cannot really tell anything at all, or can someone actually make a right answer from this picture? It turns out there is information. If I tell you, you will be able to see it. That is, since they are closer, it doesn't have a very bright core at the center. So all the other 4, if you look at the center, the light profile has a more concentrated central in the other 4 picture. For this one, the light is really flat near the center. It doesn't have a concentrated light profile. It turns out that is exactly the information that we are using when I mentioned here. You can see in this all 4 pictures, these are all really low ratio, which means they're already nearby. You can see that they don't really have any like kind of central peak. But even if you compare the left column and the right column, you can see the left column are even more smooth at the light profile near the center. And so the closeness of the galaxy actually bring the light profile less concentrated, if you will, for the dwarf galaxy at this scale. This is obviously not true for spiral galaxy, right? That's a totally different story. But for dwarf galaxy, you can actually use the light profile to tell the distance. And that is why the machine learning can pick up this kind of feature and then become kind of an accurate predictor to tell the difference of the distance of this dwarf galaxies.
Okay, so if I understand very well, okay, I guess I missed something. Like how do we bring in satellite galaxies into this whole idea of studying dark matter and dark energy?
Yeah. So the satellite galaxy coming to in several different ways. So one of the ways we do is by counting the number of satellites, and different dark matter models kind of give you a different prediction of how many satellite galaxies should be there. And so by counting the number of satellites, then we can kind of put a constraint on which one is more likely to be the dark matter model, right? So if you consider one dark matter, then you cannot have like too many satellites, for example. So that is one of the way that you can you can say, okay, it cannot be one dark matter if I observe this many satellites, right? So this is one of the way. The other way that I demonstrated is by looking at the distribution of the satellite. So again, self-intelligent dark matter and warm dark matter, they kind of leave the satellite in different parts of the system. And so by studying where the satellite sits, there's another way to distinguish different satellite systems. You also mentioned dark energy. It's a good question about how do we use satellite system to distinguish dark energy. I don't think dark energy kind of at a much larger scale. So, the satellite system is kind of live really within a kind of a high density region of dark matter. And so within that region, the dark energy, to some extent, we don't really feel the effect of dark energy. It's kind of, when you are on Earth, you don't really feel the effect of dark energy. Dark energy kind of at a very, very large scale. So I actually don't know. I don't know at this point. I think we don't have a very strong way to use satellite system to put constraint on dark energy. But who knows? As we study this further, maybe there's a way in the future.
Yeah. Okay. I guess that's all for me.
And great, thank you so much, Yao, for a marvelous talk. And thank you, everyone. We'll see you on the first Friday of November.
Thank you, Heidi. Thank you, everyone.